What you can see are several typical electrical signals representing the electrical activity of the heart, and we're looking at them on a multi-channel oscilloscope here in the coronary care unit at Charing Cross Hospital. And this program will be looking at the problems involved in getting signals into and out of electronic circuits. In the latter half of the program we'll be with loudspeakers, but for the moment let's concentrate on these waveforms, and we'll ask Dr. Green, who is the consultant in clinical monitoring here, just exactly what are these waveforms and why are they useful?
Well, these waveforms are derived from the electrical activity of the heart, and as you can see from these three written out examples, the wave shapes may vary quite considerably.
Do you have any problems getting these waveforms?
Yes, we have several. In the first place, we have to be very careful about electrical safety, and we must isolate the patient very thoroughly, both from the mass of the equipment and from the mains electricity. Secondly, we only have about 1 to 3 millivolts derived from the patient, and at a source impedance of our electrodes, which are stuck on the patient, of about 40 to 50,000 ohms. And then there's always the problem in a large hospital like this with a lot of electrical equipment of interference from outside.
So what sort of amplifier do you use then?
So therefore we use differential amplifiers with screened input leads.
Let me follow that point up because we've got a demonstration that will show that. What we've got is a differential amplifier, and I'm simulating the signal from the patient with these two connections and a further connection here, which I'm going to talk a lot more about later. Now, the simplest way of connecting to this amplifier is to earth the non-inverting input. So let's just try that. And to earth one of the incoming signal wires. We connect straight across on the other input. And what we can see on the scope is sharp pulses which simulate the signal, and the jittering that we can see is the pickup that we've induced. Now, these leads represent what could be quite long leads between the patient and the monitor equipment. So pickup is obviously a problem. Now, we've got a differential amplifier, so why not use it? Let's connect it in a differential mode. So let's disconnect this earthing wires and connect straight across to the non-inverting input. And I think you can see there that we've got an improvement already. But we'll get a better improvement if we hold the two wires together. And the reason is that the amplifier only amplifies differences between the two incoming signals. So if we can physically keep the two connecting wires close together, the pickup should be the same on both. There's one further refinement that they use, and that is to use a special cable. This is the same sort of cable. It keeps the two signal wires very close together because it's in the same covering. And at this point here, we've exposed it just to show that surrounding the signal wires is a little copper braid. And this copper braid is brought out here, and it can be connected to earth and screen the cable from some of the effects of the pickup. Let's try that one. Connecting to the source. Now we connect to the amplifier. And now you can see what the other lead was for on the incoming side. It's got a screen as well, and we connect the two screens together. And that's the best we've got yet.
Well, the differential amplifier is connected via the sticky electrodes to the patient, usually here, and a third central connector for help the common mode rejection. The cable is then taken to the machine by a screen cable, and we see here an electrocardiograph with the usual spike type waveform followed by a low frequency wave just after it. In order that the nurses may not have to keep looking at this display, we have an arrangement whereby the rate in beats per minute is derived electrically from this signal and displayed digitally here. Also, we have an alarm system so that if the rate moves out of specified limits, which can be set by this and this slider, it will sound an alarm and draw the nurse's attention.
And how is all this equipment powered?
This is all powered from the mains, but the patient is also further isolated from the main box by means of a transformer and a large gap between the two parts of the circuit.
What I want to do is to show you how we can use the transformer to get DC power for the amplifier across the isolation barrier. I'm going to use these two coils as the transformer. They're simply copper wire wound around an insulating former. In this case, I've got an AC signal going in, and we can see that here. This line is the 0 voltage reference, and if we have a look at the output from the second coil, you can see that as I bring the coils closer together, we get a signal from the other coil. This is due to the fact that the sine wave in here produces a varying flux, which induces a voltage in the second coil. And we can increase the effect of that flux by inserting a metal core. And you can see that even if I separate the two coils, we still get a signal. Now, in the case of the printed circuit board, we had circular transformers like this, the coils wound around a circular former. So this enables me to get AC power across the isolation barrier, but I want DC power. So we need a rectifier. And I'm going to use a full wave bridge rectifier, which, as you recall from Unit 7, has 4 diodes. So let me put the output from the transformer into the bridge. And have a look at the output of the bridge on the oscilloscope. Now, as you can see, in this case, the waveform is all positive, so it will have a non-zero DC value. And we can use a low-pass filter to smooth this and so derive DC power for the amplifier.
Let's just recap a minute using this system diagram. Remember, we used a differential amplifier to connect to the 2 electrodes on the patient. And of course we had to provide a power supply for this, which was isolated using a transformer, as Nick has explained. But if we go back to the amplifier, we need to get this signal from the amplifier out through the isolation barrier as well. And the way in which we do this is to use a transformer as well. There we are. The problem is that the transformer won't pass the signal as it stands because it's a low frequency signal. We need to process it to convert it to a higher range of frequencies. And we do this using a chopper. These higher frequencies pass through the transformer, and on the other side, we rectify them and low-pass filter them. And this then produces the raw signal. Well, that's the system diagram of how it works. Let's have a look at the waveforms now.
I want to show you the performance of the chopper using a sine wave as input signal. The input goes in here, and you can see the signal on the oscilloscope. Now, let's have a look at the output of the chopper. Well, that looks a bit weird. Let me slow things down first. And I'll expand the time base. Now, what the chopper is doing is to chop between my input sine wave, which has been superimposed on a DC signal, and 0. So sine wave to 0. Now let's have a look at the output of the transformer. Well, if you can see, we find that when we go from 0 to positive volts, we produce a positive pulse on the output of the transformer. And likewise, when we go from positive to 0, we produce a negative pulse. And the height of these pulses is determined by the height of these pulses. Now, if I slow the time base down, you can see that the envelope of the pulses is the input sine wave. But I've got positive and negative values. Well, I can remove the negative values using a rectifier, and I can recover the envelope using a low-pass filter. Let's turn the gain up a bit. Well, it seems to have the right sort of envelope, but because I haven't yet switched back to the original frequency. If I do that, you can see the original input sine wave.
Well, now we're back in the monitoring section of the coronary care unit, and we've shown how waveforms such as these can safely be obtained from the heart section. And the nurses here are listening in particular for the alarm which sounds when the heart rate, which is generated from these waveforms, goes out of range. But the waveforms themselves look pretty confusing to me, so I'll ask Dr. Green to explain how you can get a heart rate signal from these waveforms.
Well, the heart signal usually consists of a spike-type waveform followed by a half a sine wave at a lower frequency. Now, it happens that the spike may be either positive or, as in this case, negative. And in order to get rid of the slower waveform, we filter the signal, shown here. Then, in order to allow for negative going signals on the spike, we then rectify the signal so that we end up always with positive spikes. We then set a comparator at a fixed level along here such that every time the spike occurs, it triggers the comparator. The comparator then fires a monostable circuit which gives rise to a fixed length pulse, as here. And this also has the very useful effect that during the time the pulse is there, the monostable is dead, so that if there is any other spike waveform derived from the high-pass filtering of the original signal, it doesn't fire very rapidly straight after the first time.
Good, thank you. Now, before we go on to the next part of the program, I couldn't resist taking this opportunity and getting myself wired up and having a look at my own ECG. So, Doctor, could you plug me in?
Well, as you've probably guessed, the second part of this program is about output transducers, and in particular, loudspeaker systems. Let's have a look behind the cover. You can see it's quite a complicated system. We've got a base unit, a high-frequency unit, and a mid-frequency unit. We've come to KF Electronics at Maidstone to examine their systems approach to loudspeaker design. But let's start off with a single unit. Glyn's got a typical base unit down in the production area.
This is a drive unit taken out of its cabinet. And if we look on the back, we can see two electrical connectors. There are three main components to a drive unit. First one is a speech coil. Here it is. Coil's wound on the back here, and it comes complete with its support and the connecting wires to the terminal. The next is the cone, sort of light and flexible plastic material. This one down the end is the heavy one. It consists of the chassis, and on the back we've got a magnet. If you look very closely at the top of the magnet here, you can see a circular gap in the magnet, and it's into this that the speech coil goes, like so, making connections to the terminals. Then the cone is connected to the speech coil like that. Okay, now let's look at a simplified representation of this drive unit so that we can understand how it works. The magnet assembly is circular, with, say, a central south pole surrounded by an annular north pole. Now, removing the front of the magnet will help to make things clearer. The magnetic flux lines are radially directed from the north to south poles. The coil is attached to the cone and situated in the gap between the pole pieces, so that the flux cuts the coil at right angles to give the best sensitivity. When a voltage is connected across the end of the coil, a current flows, which interacts with the magnetic flux and moves the cone. With the polarity of the voltage reversed, current flows in the other direction. and the cone moves the other way. Now, if a varying voltage such as a sine wave is applied to the coil, the cone moves backwards and forwards, producing a pressure wave which can be heard as a sound.
Well, now let's have a look at a real system. This is a cutaway cabinet, and we can see the 3 drive units inside. And I'm using this sine wave oscillator to drive the base unit. You can see the backwards and forwards motion of the diaphragm. But I'll let Raymond Cook, Managing Director, explain the company's systems approach to loudspeaker design.
At the present time, it's very difficult to construct a high-quality loudspeaker using a single wide-range drive unit. Not only are there difficulties in obtaining an extended frequency response, but the directional characteristics become unsuitable above a few thousand hertz. It's common practice, therefore, to design a loudspeaker using 2, 3, or even more drive units, each designed to handle a narrow part of the frequency range, and to marry these together into one homogeneous frequency response. A typical arrangement using 3 loudspeakers might, for instance, look like this. We'd have a low-frequency loudspeaker covering preferably not more than a decade, a medium-frequency loudspeaker also handling about a decade, and a high-frequency loudspeaker which carries the response on to the limits of audibility. The trick is to marry these together with suitable filters in such a way as to produce a continuous collinear frequency response without the joints being audible. Now, hitherto, this has been done very much by cut and try methods, and not always very satisfactorily. But with modern computer techniques and using impulse response methods, we can do it very much more accurately and certainly very much more quickly. We begin by postulating a required frequency response in terms of sound pressure, given here in dB, against log frequency. And we call that the target function, because that is the response with which we want to finish up. We then select a suitable drive unit together with an enclosure which is satisfactory for the purpose in hand. And we measure a large batch, perhaps 100 or 200 pieces, in order to derive a mean response curve for that particular drive unit in its specific enclosure.
I want to briefly interrupt Mr. Cook for a moment. He's mentioned the term impulse testing several times. Let's see what this involves. We've set up a complete loudspeaker system next door. Basically, the idea is that we excite the speaker with a voltage pulse. And we measure the output with a microphone. The microphone output is fed, and we can display it here. I'll just bring it up. It takes a bit of time to complete the picture. There it goes. The display is voltage against time, and the total duration is about 20 milliseconds. Most of the information is contained in the beginning, and the transient dies away to 0. We can use computer to convert this display to one of frequency response. Let me do that. Again, takes a bit of time. In this case, we've got dB plotted against log frequency. And you can see that over the major portion of the frequency spectrum, the response is fairly flat. So that's the impulse test. Let's go back to Mr. Cook.
Taking that mean response curve, which might, for instance, look something like this, which would have a rising response in this section, and a far too extended frequency response beyond the required cutoff point. We then derive, by calculation, an inverse frequency characteristic, such as we see here, which not only corrects the response in the pass band, but also adjust the response at the cutoff frequency and beyond it, because we find it necessary to control the response of the combination of the filter and its drive unit to something like 40 dB below the general level in order to have a very good marriage and inaudible joints in the various sections. A typical filter looks something like this. Might, for instance, comprise 2 inductors, which we see here, a capacitor, and an attenuating resistor.
Well, Mr. Cook's shown us how a systems approach to loudspeaker design helps us to obtain a satisfactory frequency response. But there's another point that must be considered by both amplifier manufacturers and loudspeaker manufacturers, and that is that the impedance of a speaker varies with frequency. I've got a typical plot here. In this case, we've plotted the logarithm of the modulus of impedance against log frequency. You can see it's certainly not constant with frequency. You'll see how we can cope with this in the amplifier case study.